Hi everybody, it's Ms. Barkema again. I'm bouncing back on computers, so you might not see my face in all of these. But in video 1, we did density conversions. In video 2, it's going to feel like switching gears a little bit. This kind of sets you up for the math part of the unit. Video 2 is going to set you up for the conceptual part of the unit. So we are going to be doing notes on the mole. Now, the mole is going to be one of the key ideas in chemistry. It's not intuitively hard. It's just something that you want to make sure you're paying attention to, because this is really going to be a word and a term and an idea that you'll want to be comfortable with. Not just familiar with, but comfortable with. So we are going to be looking at the mole. First thing we should probably do is define this word. What is a mole? We're not talking about the animal. In chemistry, a mole is another word for a specific quantity. And it's chemistry, so what we are measuring is atoms. Quantity is probably a term you've used before and a term you know, but just to give you some ideas, a quantity is a term that we use to describe a set number. So for example, a couple would represent a quantity of 2. A dozen would represent a quantity of 12. Just like a baker's dozen would represent 13, or a decade might represent a quantity of 10. Usually decade is talking about 10 years. A mole is measuring a quantity of atoms. And that quantity isn't 2 or 12 or 10. Atoms are very small. So when we measure a quantity, we're going to be measuring a whole lot. In fact, we are actually measuring 6.02 times 10 raised to the 23rd atoms or particles. It's a big number with a big label, but it's just like the other quantities. It's a name that represents a number. The name mole represents the number 6.02 times 10 to the 23rd, and we're talking about atoms or particles. For example, if I had 1 mole of copper element, I would have 6.02 times 10 to the 23rd. Copper is an element, so we can call them atoms of copper. If I had 1 mole of iron in my hand, I would have 6.02 times 10 to the 23rd atoms of iron. If I had 1 mole of water, I would have 6.02 times 10 to the 23rd. Now, water is not an element, so it's not an atom, so we could say particles or molecules of water. So it's just a quantity. It's just a really, really big quantity. And we need to use a really, really big quantity because atoms are really, really little. And when we're measuring atoms, we're usually measuring a whole lot. So our quantity talks about a whole lot. Now, why this number? This is not just some random, really, really big number. This number was, I'm not sure if it was discovered, is probably not the right word. The first person to really point out the significance of this number was Avogadro. So this is very frequently called Avogadro's number. And the reason this number is so special is because the weight in grams of 1 mole of any substance is equal to the weight in AMUs of the same stuff, of that same stuff, of 1 mole of that substance. If you don't remember, this weight in AMUs, that is the atomic mass on the periodic table. So, for example, the periodic table has 118 elements. All of those elements have little atom cards. If you were to look at the atom carbon, you would see that on carbon's atom card, it is atom number 6, and it has an atomic mass of 12.01. This would be what you would see on the periodic table. That means that 1 mole of carbon, which would contain 6.02 times 10 to the 23rd atoms of carbon, would have a weight of 12.01 grams. So really, what this quantity allows us to do is be able to convert between atoms and grams without trying to use the weight of an individual atom. This becomes a very, very powerful number because we can go from atoms to grams, and we can also go backwards from grams to atoms. But for now, we're just going to focus on this atoms to grams and grams to atoms connection. And then in the future, we'll add some other substances and other conversions that we can use that involve this quantity. Now, if this theoretical stuff confused you just a little bit, hopefully these examples will start to help clear it up. We are going to be doing 2 different kinds of examples. Today, we're going to be focusing really on the first part of this video. So talking about the conversions just between moles and atoms. And the second video, we'll focus on the conversion between moles and atoms and grams. But for today, we're just going to focus on converting between moles and atoms. Atoms might also be particles if we're looking at compounds and not single elements. Example 1, I want you to convert 30 moles of calcium to atoms. Same stuff as dimensional analysis, same skills that we've been working on with density conversions. Start with what you know. I know I have 30, moles is abbreviated as MOL, just chop off the ES, of calcium. And I know my end goal is to get to atoms. How do I get from moles to atoms? By using the 6.02 bridge. Moles of calcium needs to cancel out, and then I can go to atoms of calcium. Using the moles just like we use a conversion factor. 1 mole of a substance contains 6.02 times 10 to the 23rd atoms of that substance. Take that, plug it into your calculator. 30 times 6.02 times 10, which is that EE key, to the 23rd. And I end up with 1.806 times 10 to the 25th. Rounding that off, 1.8 times 10 to the 25th atoms of calcium. Being careful to keep the full label throughout the entire problem. Keeping calcium, making sure it ends up in your label as well. So that's one direction. From moles to atoms, the opposite would be from atoms or particles to moles. So example 2 is going to show that. And we are going to convert 1.00 times 10 to the 20th molecules of water to moles of water. Be careful with the labels. So this one was chosen on purpose. Molecules and moles can look really, really similar, but they are different. Identify what we're starting with. I'm starting with 1 times 10 to the 20th molecules of water. And my goal is to get to moles. I can do that through our mole bridge. Molecules of water needs to cancel. And I get 2 moles of water. The 1 will always go with the mole label. The 6.02 will always go with the atoms or molecules. And all that's left is to plug it into a calculator. 1 times 10 to the 20th. This number's on the bottom, so we're going to divide. 1 times 10 to the 20th, divide 6.02 times 10 to the 23rd. I should end up with a decimal. And I do. I'm going to take that and turn it into scientific notation. 1, 2, 3, 4, 5. Wait, I don't want to go back that far. 1, 2, 3, 4. 1.66 times 10 to the negative 4th moles of water would be your final answer. Now, today for your practice problem, since we're just focusing on the moles to atoms bridge, they're going to be this type of setup. Give what you know, use the mole bridge, 1 mole per 6.02 times 10 to the 23rd molecules or atoms to get you to the other side of your bridge. So good luck with that. Don't try and overcomplicate the problem. Use these examples and make sure the 1 is always with the mole.